Imagine you've got all these pieces of a huge ancient puzzle. They're just scattered everywhere. Some look like they fit, others, well, they just seem random. That's kind of what early chemists were facing with the elements. We know matter is elements, compounds, mixtures. Today there are 118 known elements, 94 found in nature, each completely unique. So the massive challenge was, how do you possibly organize this incredibly diverse collection? And that's what this deep dive is all about. That amazing journey, scientists using observation, trial and error, and some really brilliant thinking to bring order from what looked like total chaos, which eventually led us to one of the most famous, most powerful tools in science, the periodic table.
So, okay, in the very beginning, way before the big theories, chemists were just trying simple sorting. Like if you have a messy shop, you start with the obvious groups.
Exactly. The very first attempts were super basic, just grouping into metals and non-metals.
A start, but clearly not enough to really get what was going on with them.
Definitely not, just a first step. Then, jump forward to 1817. Johann Wolfgang Dobereiner, a German chemist, he spots something. Well, interesting.
Yeah, he wasn't just sorting anymore. He was looking for actual relationships between elements.
And he came up with these groups of three with similar properties, called them triads.
Right. And the clever bit was, he noticed a pattern with their atomic masses, if you arrange the three by increasing mass.
The middle one's mass was almost bang on the average of the other two.
Pretty much, yeah, like lithium, sodium, and potassium. Lithium's 6.9, potassium's 39.0. Average those.
You get 22.95, and sodium is 23.0. That's incredibly close.
It really is. And he found others, too, like calcium, strontium, barium, and chlorine, bromine, iodine. He saw a little piece of the order.
But just a piece, right? That was the problem.
That was the limitation, yeah. He only found 3 clear triads among the elements known then. So while the idea was a breakthrough that patterns existed, his system wasn't comprehensive enough. It couldn't classify everything.
Okay, so a good idea, but limited reach. What pushed people to look for something bigger after that?
Well, the fact that even a few triads existed suggested there had to be some deeper underlying order. A natural law just waiting to be found. It really spurred people on.
Which brings us to John Newlands, an English scientist around 1866.
Yes, Newlands. He took a bolder approach. Arranged all 56 known elements then by increasing atomic mass. Hydrogen first, thorium last.
And this is where it gets a bit musical.
Right.
The law of octaves.
Ah, yeah, the musical analogy. He noticed that every 8th element seemed to have properties similar to the first one, like notes in a scale, do re mi, that kind of thing.
So lithium and sodium were similar, sodium being the 8th after lithium. Beryllium and magnesium too.
That was the observation.
Okay, catchy name, but you flagged this earlier. This is where it gets really interesting because it had some pretty major flaws.
You're right. Big limitations. It really only worked well for the lighter elements, up to calcium, basically.
Beyond calcium, the pattern just
Fell apart, completely broke down, yeah. The music stopped, so to speak, for the heavier elements.
And he also made this huge assumption, didn't he? That only 56 elements existed, period. No more would ever be found.
Which, of course, was wrong. New elements started popping up pretty quickly after that.
And to make things fit his table, he kind of had to force it sometimes.
He did. He made compromises that really showed the cracks. Sometimes putting 2 elements in one slot. Cobalt and nickel got squeezed together.
And grouping things that didn't belong.
Exactly. He put elements with really different properties under the same note. So cobalt and nickel ended up in the same column as fluorine, chlorine, bromine. Chemically, that makes no sense.
While iron, which should be near cobalt and nickel, was miles away in his table.
Right. And then later, when noble gases are discovered, they just didn't fit anywhere. His law of octaves became, well, irrelevant. A nice idea, but not the answer.
So, a dead end. Which leads us to Dmitry Ivanovich Mendeleev. Russian chemist, 1872. This feels like the really big leap.
Oh, absolutely. Mendeleev's contribution was monumental. The most significant early step towards the table we know.
Okay, so let's unpack what he did. He started with 63 known elements.
And crucially, he focused not just on atomic mass, but really zeroed in on their chemical properties.
How they reacted, basically.
Especially how they formed compounds with hydrogen and oxygen, the hydrides and oxides. He saw that the formulas of those compounds gave a really consistent way to group elements.
And the story goes, he wrote each element's properties on a card and sorted them.
That's the famous anecdote, yeah. Like playing chemical solitaire, pinning them on his wall, looking for the patterns.
And the key insight was,
he saw that when you arrange the elements by increasing atomic mass, Similar physical and chemical properties reappear periodically, at regular intervals.
Which led to his periodic law. The properties of elements are the periodic function of their atomic masses.
Obviously. And his table had vertical groups for similar elements and horizontal periods.
And his achievements here were just remarkable. He wasn't afraid to bend his own rules slightly, was he? For chemistry's sake.
No, he prioritized chemical sense, like placing cobalt, mass 58.9, before nickel, mass 58.7. Mass-wise, it's wrong. But chemically, it put them in the right groups with similar elements.
But the really bold moved the gaps, leaving empty spaces in his table.
That was sheer genius and incredibly confident. Instead of seeing gaps as flaws, he said, these are elements that haven't been discovered yet.
Wow. And he predicted their properties.
He did. He even named them using the Sanskrit prefix eka, meaning one. So eka boron, eka aluminium, eka silicon, predicting elements that would fit below boron, aluminium, and silicon.
And the eka-aluminium story is amazing, right, with gallium?
Absolutely spectacular validation. When gallium was discovered later, its properties atomic mass 69.7, oxide G2O3, chloride GCl3 were astonishingly close to Mendeleev's predictions for eka aluminium, mass around 68, oxide E2O3, chloride ECl3.
That must have convinced a lot of skeptics.
Oh, it did. It really cemented the acceptance of his table. It showed predictive power, not just organization.
And another big plus when those noble gases, helium, neon, argon, were found later.
They could be slotted into a whole new group without messing up the existing order. It showed the framework was robust and adaptable.
Still, even Mendeleev's brilliant table had some lingering issues, loose ends.
It did. For one, hydrogen. It just didn't quite fit neatly anywhere.
Because it acts a bit like the alkali metals sometimes, forming salts like NaCl.
Like HCl, yeah. But it also acts like the halogens exists as H2, forms covalent bonds. Its position was, and still is, a bit ambiguous. Mendeleev couldn't quite nail it down.
And then came isotopes, discovered much later.
Right. Isotopes were a problem for a mass-based system. They have the same chemical behavior, belong in the same spot, but have different masses. His table couldn't naturally account for that.
And one more thing, the atomic masses didn't always increase perfectly regularly, did they? Made it hard to know exactly how many elements might be missing between heavier ones.
That's right. There was still a bit of uncertainty there.
Okay, but then came the final piece of the puzzle, the thing that led to the modern periodic table we use now. Henry Moseley, 1913.
Yes. Moseley's breakthrough was fundamental. He was looking at X-rays emitted by elements.
And he showed that the atomic number, the number of protons in the nucleus, which we call Z, that's actually the more fundamental property than atomic mass.
Exactly. It defines the element. And this led straight to the modern periodic law. Properties of elements are a periodic function of their atomic number.
And the key is, atomic number increases by exactly one integer from element to element. Nice and regular.
Perfect sequential order. No more ambiguity like with mass.
And this just solved Mendeleev's problems, didn't it? Like the cobalt-nickel thing.
Instantly resolved. Cobalt has atomic number 27, nickel is 28. So cobalt naturally comes before nickel when ordered by atomic number. No need to force it. It aligns perfectly with their properties.
On the isotope issue.
Gone. Isotopes of an element all have the same atomic number, the same number of protons. So they automatically belong in the same position. The system just works.
And predicting missing elements became easier too.
Much easier. Since atomic number increases by whole numbers, you know exactly how many integers, and thus how many potential elements, exist between any two known elements.
What about hydrogen? Still tricky.
Still unique. But the modern table provides context. We see why it's debatable it has one valence electron, like group 1 alkali metals, but it's also one electron short of a full shell, like group 17 halogens. Its position reflects its dual nature.
Okay, so let's look at the modern table's structure. 18 vertical columns, the groups, 7 horizontal rows, the periods.
And the columns, the groups, are key. Elements in the same group have the same number of valence electrons, those outermost electrons involved in bonding.
Which is why they have similar chemical properties. It all comes down to those outer electrons.
Precisely. And as you go down a group, you're adding whole new electron shells, so the atoms get bigger.
And the rows, the periods, what do they tell us?
Elements in the same period have the same number of occupied electron shells. As you move left to right across a period, you're adding one valence electron at a time. Each new period means you start filling a new outermost shell.
And the length of each period, 2 elements in the first, 8 in the second and third, 18 in the next two, 32 after that? That's not random either.
Not at all. It's directly related to how many electrons each shell can hold. It follows that 2n formula from quantum mechanics. First shell, N1, holds 2, second N2 holds 8, and so on.
Wow, so the table's very shape reflects fundamental physics.
Absolutely. It's incredibly elegant. What's fascinating is that in Elements Address, its group and period tells you so much about how it's going to behave chemically, its reactivity, how it bonds.
And we see clear trends because of this structure, like valency, the combining power.
Yes, valency follows predictable patterns. It's determined by those valence electrons how many an atom wants to gain, lose, or share to get a stable configuration. It generally increases and then decreases across a period and is often similar down a group.
What about atomic size, the radius?
Clear trends there, too. As you go across a period, left to right, the atoms actually get smaller.
Smaller, even though they're getting more protons and electrons.
Yeah, it seems counterintuitive, but the increasing positive charge in the nucleus, more protons, pulls all the electrons in that same outer shell closer. Stronger attraction.
Okay, but down a group, they get bigger.
Definitely bigger. Because you're adding entirely new electron shells further out from the nucleus. The outermost electrons are just physically farther away.
Makes sense. And metallic versus non-metallic character.
You can basically see it on the table. Metals like sodium, magnesium, iron are mostly on the left and in the center.
And nonmetals like oxygen, chlorine, sulfur are on the upper right.
Correct. And there's that kind of zigzag line separating them.
Ah, the metalloids. Boron, silicon, germanium, arsenic. Those ones.
Exactly. They sit on that border and show properties of both metals and nonmetals. They're semiconductors mostly.
And the tendency to act like a metal to lose electrons.
That metallic character decreases as you go across a period. Harder to lose electrons when the nucleus is pulling them more strongly.
But it increases as you go down a group.
Yes, because those outer electrons are further away, less tightly held, easier to lose.
And non-metallic character, the tendency to gain electrons would be the opposite trend.
Precisely. Increases across a period, decreases down a group. And these trends even help predict other things like whether an element's oxide will be basic, like metal oxides usually are, or acidic, like non-metal oxides tend to be. It's all interconnected.
So what a journey. We've gone from very simple lists like metals and non-metals.
Through Dobereiner's Triads, seeing the first hints of patterns.
Newlands Octaves, a good try but flawed.
Then Mendeleev's incredible insight, arranging by mass, focusing on chemistry, leaving gaps, making predictions. Just amazing foresight.
And finally, Moseley nailing it down to atomic number, giving us the modern periodic table that organizes everything so perfectly and predicts behavior.
It's really quite a story. So what this all means is the periodic table isn't just some chart to memorize for a chemistry test. It's really a testament to this persistent human drive to find order in the universe, to uncover the underlying rules.
It's a narrative of science itself, building on previous work, making bold guesses, refining ideas, and arriving at this unifying principle that just revolutionized chemistry.
Absolutely. It underpins so much of how we understand matter.
Okay, so final thought here. The periodic table is often called the alphabet of chemistry. And we've seen how its structure reflects really fundamental things like electron shells and nuclear charge. So if we could somehow, hypothetically, observe a set of totally alien elements from another galaxy, do you think their version of a periodic table would end up having the same basic organizational principles based on similar quantum rules? Or could chemistry work so differently elsewhere that their system would be completely unimaginable to us?